Welcome to Pavinars, webinars for the pavement community. My name is Andrew Braham, and today we'll be talking about the influence of binder grade, gradation, temperature, and loading rate on our curve of asphalt concrete. This is work that Dr. Shu Yang performed on his dissertation research, and it's based off the paper that he wrote titled Influence of Binder Grade, Gradation, Temperature, and Loading Rate on Our Curve of Asphalt Concrete. Dr. Yang obtained his Bachelor's of Science from Southeast University in Civil Engineering and also his Master's of Science in Highway and Railway Engineering, both at Southeast University in Nanjing, China. And he received his Doctorate of Philosophy at the University of Arkansas in Civil Engineering. And a link to his LinkedIn profile can be found below in the description. Before we get into our curves, let's talk a little bit about fracture testing fundamentals. So in the world of asphalt concrete, we use fracture testing to look and quantify cracking susceptibility. And this can include both crack initiation and crack growth. There are various traditional outputs, including fracture energy, stress intensity factor, J integral, among others, and these are all used in order to try and better understand the cracking of asphalt concrete. And there are different fracture testing geometries. You have the single edge notch beam, which is shown here. You also have a semicircular bend and a disc-shaped compact tension. Now, while there are different geometries, all of these tests can capture fracture energy, stress intensity factor, and J integral. When we look at collecting data during fracture testing, we're usually collecting a load and a displacement, and this displacement can either be a load line displacement, which is essentially the vertical displacement during the test, or it can be a crack mouth opening displacement, so how much the mouth of the crack is opening, or it could even be a crack tip opening displacement. But regardless, you have some sort of load versus displacement, and you can measure these curves. And you can see for a brittle asphalt concrete mixture, you usually have relatively high and early peak loads and a very steep softening curve. And for ductile materials, you generally have a lower peak load, but a much longer softening curve. And we had mentioned before that fracture energy is a common output, and you calculate fracture energy, which can be represented by G sub F, as taking the area under the load displacement curve and dividing it by the ligament area of the sample itself. So here P equals load, U equals displacement, and A sub Lig, the ligament, is the specimen thickness times the length of the crack. So again, if we have our load displacement curve, which we saw previously, we're simply taking the area under this load displacement curve, and then we're dividing that by the ligament area, or the specimen thickness times the length of the crack. And a very common unit for fracture energy is joules per meter squared. Now there's some disadvantages to fracture energy reporting, or the stress intensity factor or the J integral. These all only give a single number. Curves can give the same fracture energy, but they can have very different shapes. And these single numbers, such as fracture energy, do not incorporate pre and post-peak load behavior. Now the flexibility index does take a look at the slope of the softening curve at a point, but again, all of these numbers are simply taken at a point. In addition, it only incorporates a single testing temperature. And fracture curves look very different when they're at different temperatures. Because asphalt concrete is a viscoelastic material, it behaves very differently as both the temperature and the rate of loading changes. So how can we get some more information? And the first round that we tried was a concept called master fracture curves. And essentially what we did with the master fracture curve is we found the cumulative energy. So these are the load displacement curves, but instead of having the energy plotted over time, we simply took the cumulative energy. And then we shifted the displacement curves. And here we used CMOD, crack mouth opening displacement. And you can see that as the temperature increased during testing, the cumulative energy increased, and also the total displacement increased. And then what we did is we simply made one single curve and we fitted a function to that. And if you're interested in learning more about master fracture curves, you can see our Pavinar that was recorded on February 19th, 2020, and that talks about master fracture curves. Now, another option, and this is what Dr. Yang explored, was the resistance curve, or an R curve. So R curves are quite common in concrete, rocks, ceramics, adhesives, teeth and bones, all these different types of materials. So this is certainly not a new concept, but we found very little work done with it in the world of asphalt concrete. And here we look at fracture resistance as a function of crack extension. So again, instead of just looking at one single point, we're taking a look at the whole curve. And there's three key components that we extracted from the R curves that we collected. The first is the crack initiation, the second was the crack propagation, and then the third was the fracture energy. So we did end up actually quantifying the fracture energy, but we also got the crack initiation and crack propagation as well. A benefit about R curves is that you can calculate the R curves for linear elastic materials, for plastic elastic materials, and for time-dependent materials like viscoelastic materials, which is what asphalt concrete is. But as I mentioned, there's been very limited research found in applying these R curves to asphalt concrete. So here's an example of some data that we collected. And this is an example of three replicates, and those have the circle, squares, or triangles associated with them. And then you can also see we calculated the average of these three curves to get a smooth and representative curve. Now let's take a look at those three characteristics that we can extract from the curve. The first is the crack initiation, which is the cohesive energy, and that is a point, and that is the point when you leave the y-axis. So you can see in this curve, the cumulative fracture energy continues to increase with zero crack length extension, and this is all cohesive energy. So how much energy is going into starting to form the crack? And you can see it peaks out just around 800 joule per meter squared. The crack propagation, this is the slope of the line as the crack grows, and this is also called the energy rate, but this gives you an idea of how quickly the crack is forming. And then finally, the fracture energy is at the end of the test, and it's simply the point at the maximum cumulative fracture energy. Now, in order to calculate the crack propagation, you can see we obviously used some smooth data here. And what we did is we simply took the fracture energy, we subtracted the cohesive energy, and we divided it by the total crack extension. Now, this is the R curve was the fundamental part of Shu's dissertation, and he went into a lot of examinations of what was happening, for example, when this cumulative fracture energy just jumped up completely. But for this research here, our crack propagation, the energy rate is simply the fracture energy minus the cohesive energy divided by the total crack extension. So in this study, Dr. Yang explored the influence of asphalt binder grade. He looked at a PG64-22, which was a neat asphalt binder, and a PG76-22, which is a SBS polymer modified. He looked at two different nominal maximum aggregate sizes, or NMAS, 9.5 millimeters and 25.0 millimeters. So here in the state of Arkansas, that is a typical surface course and then a typical binder or base course. He looked at three testing temperatures. He looked at 24 degrees Celsius, 0 degrees Celsius, and negative 24 degrees Celsius. So these are very common temperatures that fracture tests are run at. And then he looked at two different loading rates. 0.03 millimeters per minute and 1.0 millimeters per minute. And the loading rate of 0.03 millimeters per minute is very common for tests run below freezing or below 0 degrees Celsius. And then the 1.0 millimeters per minute is common for the fracture test run at ambient temperatures. So the low temperature SCB, semicircular bend fracture test, is run at 0.03 millimeters per minute around minus 24 degrees Celsius. It's dependent on the low temperature binder grade, whereas the iFit test and the LTRC fracture test is run with 1 millimeter per minute at positive 24 degrees Celsius. So what Dr. Yang looked at was how do these four factors influence the cohesive energy, the fracture energy, and the energy rate? Well, let's step through each one individually. So for the asphalt binder grade, all of these graphs that you'll see on the following slides, we have the fracture energy, the cohesive energy, and the energy rate on the X and Y axis respectively. And then we took a look at the two different levels that we were looking at. So here for the fracture energy, the PG76 minus 22 is on the Y axis and the PG64 minus 22 is on the X axis, and everything else is the same. All we did was change this one single binder grade. And you can see that there really doesn't seem to be any consistent trend with fracture energy. The two binders, they kind of bounced back and forth, but sometimes the fracture energy was higher for the 64 minus 22, sometimes it was higher for the 76 minus 22. The cohesive energy, here there seem to be a couple more data points above the line of equality, which means that maybe the 76 minus 22 had slightly higher cohesive energies, and it could be influenced by that polymer in the asphalt binder. And here with the energy rate, it's very clear that the 76 minus 22 has a higher energy rate because almost all the data falls above the line of equality. So from an asphalt binder grade perspective, the PG76 minus 22 does appear to be more resistant to crack initiation and more resistant to crack propagation than the 64 minus 22. The next factor that we looked at was the aggregate size. So here the 25 millimeter nominal maximum aggregate size is on the y-axis, and the 9.5 millimeter nominal maximum aggregate size is on the x-axis. Here we see that the larger aggregate had slightly higher fracture energy. The cohesive energy or the crack initiation was not as clear. The data kind of bounced back and forth in between. And for the energy rate, the larger aggregates had a slightly higher energy rate, especially at those lower energy rates. Now there were a couple outliers up there on the top, but in general we felt that the larger aggregates had slightly higher energy rates. However, with all of this data, really the larger versus smaller aggregate size was not quite as clear as the asphalt binder data. Now the test temperature, however, was very clear. Here we have 0 degrees Celsius on all the y-axes and minus 24 degrees Celsius on all the x-axes, and you can see all of the data is above the line of equality. Therefore, there is higher fracture energy, cohesive energy, and energy rate with the higher temperature. Now you'll notice that there's no data shown for positive 24 degrees Celsius, and that's because there were no macro cracks initiated at positive 24 degrees Celsius. Dr. Yang used digital image correlation to measure the crack lengths as they grew, and there were no macro cracks at positive 24 degrees Celsius, and the damage actually was formed by creep damage of the sample. So we weren't really able to quantify the fracture energy, the cohesive energy, and the energy rate at positive 24 degrees Celsius. And this is something that I think the pavement community should be very aware of, is that because asphalt concrete is a viscoelastic material, at the higher temperatures and lower loading rates, often you don't get a fracture test. It is more of a creep test. And this data here shows that because we were only able to collect the fracture energy, the cohesive energy, and the energy rate at 0 degrees Celsius and minus 24 degrees Celsius. Now, finally, the loading rate. We did not see any real trends with the fracture energy or the cohesive energy with loading rate, but here the lower loading rate had a higher energy rate. So the loading is not as clear as temperature. it is a little more similar to asphalt binder and the aggregates. And something that we could think about is the concept of time temperature superposition. So we know that for bulk properties such as dynamic modulus, we can use time temperature superposition to quantify the behavior of asphalt concrete. But when we look at this data, we can see that there was an influence of temperature, but there was not as clear of an influence for loading rate. So when we're thinking about time temperature superposition with cracking, perhaps we can start getting some ideas about this concept that the testing temperature is more influential than the loading rate, at least with the data that we collected here and how each factor was set up. Dr. Yang also performed an ANOVA analysis, and any p-value less than 0.05 is considered significant. And you can see here we have the fracture energy, the cohesive energy, and the energy rate going along that top row. And then the far left column, we have binder grade, nominal maximum aggregate size, temperature, and loading rate. And you can see the only statistically significant influences were found on the binder grade. So each test had 4 replicates, and only the binder grade was statistically significant with a 95% confidence. So in conclusion, for our curves were able to capture fracture energy, cohesive energy, which is crack initiation, and energy rate, which is crack propagation. The polymer modification had a higher crack initiation. The larger aggregate had a higher fracture energy, cohesive energy, and energy rate. The higher testing temperature, 0 degrees Celsius, had a higher fracture energy, cohesive energy, and energy rate versus minus 24 degrees Celsius. And then the lower loading rates had a higher energy rate. So in conclusion, we believe that the R curves do show promise for quantifying the cracking in asphalt concrete. Now, this was a relatively limited study, but we think it's something that deserves a little more attention. So if you're interested in learning more, I encourage you to look at the full paper, which was published in Construction and Building Materials. And here is the link to the DOI, and that is also found down in the description below. So both Shu's LinkedIn link and also the DOI link can be found in the description below. But here's just a fun picture of Shu and I at the Great Wall at the Mutianyu section, just outside of Beijing. And as always, we're having a good time, working hard, but also having a good time. So thank you very much. I hope you have a great day.